Hey everyone, it's Dr. Hawkins. Today we're going to do week 10, chapter 8. These some answers to those questions you submitted through discussion forum. So we'll start with number 2. Number 2 says, which process releases energy? So when you think about releasing energy, this is the idea of becoming noble gas-like. And that's going to make them happy. So if you release that happiness, that's going to be when you form a bond and trade electrons with a partner, so that you're both noble gas-like. The opposite is true, and you might see this one in the true and false later. If you're going to break anything, it requires energy, not releases. So if you break a window, it requires energy to do that. As we look at number 7, number 7 is combustion. So it's good practice to do this. It's a pretty decent chunk of the exam. So when you see something, and this says which one is combustion, so look at them and think who has O2, CO2, and water. That's going to tell you very quickly combustion in particular, because they always have those three. Notice some other ones might have water or might have O2, but it has to be in that kind of order in order to be combustion. For practice though, notice this one has two partners, two partners, two partners, two partners. That's a double replacement. Here we have only one reactant, so that gives that one away as a decomposition. And over here you have this one trading with this one, kicking this one to the curb, and that's single replacement. And the reason we call that single replacement is notice aluminum's by itself and iron's by itself, no partners either way. So use those kinds of clues to help you with those kinds of reactions. Same kind of clues we can use here in number 9. Number 9 gives us a married couple, and notice the potassium and the barium switched. We have a whole lab based on this idea. And then barium is now a sulfate, potassium is now chloride. They switched both partners, so that's a double replacement. As we move on to other kinds of questions like these with spectator ions, you're going to need your solubility table. That's on page 105 of our lab book, so I'll give you a moment to dig that out now so you can hit pause.
Ready?
Yep. Alright, so hopefully you found your table. We used it through the entire experiment 16, which some of you hopefully have started and maybe finished. Things to look for here is if you're in these yellow highlighted regions, you're going to be always soluble in water. That's an entire section of the homework and the matching later. You're always a spectator ion, and you never precipitate. Those will answer a tremendous amount of questions. Just by knowing the ones in yellow, you probably have enough to answer every single question. There's a few that pick on a halide or a sulfate or a hydroxide in particular. Just remember those have exceptions. The exceptions to the hydroxides are typically just the ones in yellow. There are a few additions like calcium and barium that sneak in there too. But mostly things can be answered from those yellow categories, so we'll be mentioning those quite a bit. And again, this is on page 105. So as we look at this problem, it says spectator ions. So if it's a spectator ion, think about the ones in yellow. If you're a spectator ion, you're probably in group 1, you're probably ammonium, and then the negatives are acetate and nitrate. So let's just look for those first. And we see there's a nitrate, there's a potassium, and the spectators are the ones that remain soluble in water. And that's what we want. So notice here, some of the ones in yellow, potassium and nitrate. This happens to be our solid, our precipitate. And then one thing good about this reaction is lead and nitrate was a reactant. And because it's a reactant, we don't even care about it yet. It hasn't had a chance to be a spectator yet. And the same thing for potassium iodide. Those are reactants, and reactants are never answers in double replacement reactions. The answers are always over here, so you really only have 2 choices in these questions, not 4. Either have the solid or potassium and the nitrate, which stay water soluble. That's the answer in this case. But again, let's prove it. Here was potassium, always a spectator. Here was nitrate, always a spectator. And the reason that we stayed away from the lead chloride in this case, notice that was lead iodide in this case, halogens have exceptions, and one of the exceptions happens to be lead. So definitely this table going to be to your benefit to use it on the exam and all throughout this homework. If you weren't using it, you're definitely making it much harder than it needed to be. Very similar kind of question here. We have calcium hydroxide, and we have hydrobromic acid. When you add those together and you double swap, you get calcium bromide, and you get water. Water is our liquid, so there's no solid. This is a neutralization reaction. It's a special type of double replacement that we talked about, and it's at the end of experiment 16, 4 or 5 times. So again, because these are reactants, get rid of those if they're listed. So calcium hydroxide, reactant, get rid of it. Hydrogen and bromide, reactant, get rid of it. So really your only answers are here. And if they want to know who is, in this case, a spectator ion, it's the only one that's not water, and that's calcium and bromide. So again, you're using those clues, reminding yourself that you're not worried about reactants. Reactions haven't been mixed together yet, so they can't be a spectator if they haven't seen the other ions that they could mix with in the other beaker. As we go down to the bottom, we're going to see some examples of balancing chemical equations. So some of these are very tedious and very long. I don't want to kill a bunch of time in this video doing each one of these. We're just going to jump to the actual answer, which is D. As you balance this one, you'll notice that you have 2 carbons, so you're going to want 2 carbons over here, because that'll give us a 2. You have 2 hydrogens, and that already matches the 2 hydrogens. You have 2 oxygens here. You have now 4 here, and only 1 here. So the problem with that is now you have this odd number that you can't fix. And this really happens only with combustion problems. If this happens for combustion, you can double it. By doubling this, you're going to get 4 carbons. You're going to have to now turn this 2 into a 4, and that'll give you 4 carbons. It'll also give you 8 oxygens. This 2 also gives you 4 hydrogens. By taking a 2, and this is where no longer are we a odd number, you get 4 hydrogens. So far so good. 4 carbons, 4 carbons, 4 hydrogens, 4 hydrogens. And then notice now we have 2 oxygens, but now 8 plus another 2, so we have 10 oxygens. We have to think, how can we get 10 oxygens over here? Well, that's going to be with a 5. So this is a 2 to 5 to 4 to 2, none of which has a 6. The other ones are going to be the ones in that issue. So you can work through the other ones for practice. I just didn't want to kill 5 minutes going through each one. But this one definitely the one that doesn't have a 6 to answer that question. Number 21 says balance this equation, and they want specifically the same kind of order we came up with over there. So notice there's 2 irons here, only 1 here, so we could put a 2 here. If we do that, notice we only have 1 choice, so maybe we're going to have to change that. We have 3 oxygens and 3 oxygens, and then we have 2 aluminums, so we're going to need 2 aluminums. So 2 irons, 2 times iron, 3 oxygens matches 3 oxygens. They're both a +3, which makes this a little bit nicer. And then a 2, so that's a 1-2, 1-2 kind of reaction, which happened to be the only one that gave us that 2 in the end for our question. Very similar down here. We have the same issue going. So oftentimes I like to start with the biggest and the scariest. The reason this is the biggest and scariest is because it has numbers inside and outside the parentheses on both partners. If we do that, we're unlikely to have to erase. So if we have 2 aluminums, we're going to need 2 aluminums. If we have 3 chromates, we're going to need 3 chromates. That's 3 times the chromate and the potassium. So that gives us 3 times 2, which is 6 potassiums. We need 6 potassiums there. We already had 2 times 3 nitrates, which is what we have now when we have 6 times the 1. So we have 6 times both potassium and nitrate, which matches. We have the aluminum, so this is just a 3, 2, 1, 6. So 3, 2, 1, and 6. A lot of students forget that 1, it's imaginary. That's going to give you 12 that we want in this one. 24 says, which of the following is least soluble in water? So oftentimes what I like to do instead is go to those in yellow. If we know those in yellow, we can know who's most soluble in water. We can get rid of those answers immediately, and then it gives us fewer choices to actually dig through. So I like remembering the 5 that never precipitate, that always spectate, and that are always water soluble. So this one says least soluble. So we're looking for potassium loves water, sodium loves water, nitrate loves water. That's 3 up here in this magic little category of 5. They always love water. If we recognize those first, we're recognizing that the only one left is the answer, and that's calcium sulfate. Again, we can look down here with sulfates and see that calcium is an exception, and that's why it's water insoluble as a precipitate. That category is a water insoluble, no longer spectator, now a precipitate kind of category. Which hydroxide is water insoluble? Same idea. Find the ones that are always water soluble. Those are going to be things like sodium. Because it says water insoluble, we're getting rid of sodium because it is super water soluble. And that's really the only clues we have here. So we really only narrowed our choices down to 1. Hydroxides is in this bottommost category. And it says that they're usually precipitates. That's true except for group 1. We just only had sodium. But also they say calcium and barium. So let's see if we can find those, because those 2 are water soluble. Here's our barium, here's our calcium. The only one left over is the water insoluble aluminum hydroxide. In 29, they want to balance a acid-base reaction. So a lot of these are in the lab. So this takes potassium hydroxide with sulfuric acid. And when we do the double replacement here, we're going to switch the K and the H because they're both plus charges. We get potassium sulfate and we get water. So as we balance this, we notice that there's 2 acids. We're going to need 2 bases to balance it. That'll match our 2 that we have over here. We also have 1 sulfate, and we kept 1 sulfate, but we do have 2 bases and we do have 2 acids. That's going to give us 2 waters. So when they say what are the moles of potassium hydroxide, that's just the 2. Neutralize how many moles of acid, that's just an imaginary 1. So this is a 2-to-1 reaction that we're looking for here in number 29. Here with calcium hydroxide, we have a very similar kind of process, but now we have a group 2 metal, so it has 2 hydroxides. We'll see that in our next chapter as well. Still has sulfuric acid. Here we're going to get a perfect match of calcium and sulfate. That's a +2, -2, and a water. I like writing water as HOH because you see that acid and that base separated. H2O makes it a little more difficult to see that. Here we have 2 bases and we have 2 acids. That's a perfect match to make 2 waters. We have 1 calcium, 1 sulfate, 1 calcium, 1 sulfate. So this one is a 1-to-1 reaction, not a 2-to-1 reaction. So again, we're stealing this imaginary 1 and this imaginary 1. Moles is just a fancy name for coefficients. This one actually works the exact same way. It says 2 sulfuric acids to every 1 sodium hydroxide. Sulfuric acid is H2SO4. Sodium hydroxide is NaOH. When you do the double replacement, you switch the partners in front. So we get sodium sulfate and we get water. So notice it is 2 acids to 2 bases. So 2 H's, 2 OH's will be 2 H's, 2 OH's. Sodium already has a 2, that matches. 1 sulfate, now we're matched up. So this is actually a 1-to-2. This says 2-to-1, so this one is false, and that's why. Even though these weren't asked, a couple of things to think about here. This was the wife swap kind of reaction. So look for that. Combustion is the somebody plus O2 gives you CO2 and water. So look for that. Decomposition is going to have 1 reactant. So we call that a divorce. Combination is the reverse. It's going to have 1 product. We called that a marriage. And then single replacement was you have an element before and after, so we called that the home wrecker. So look for elements by themselves before and after. Nobody's, not both are partnered up and before and after like a typical wife swap kind of reaction. As we look at this section here that was questioned on in the discussion forums, we need to balance. So it takes a lot of practice. There's a tremendous amount of practice in the supplemental labs in the back, specifically I think it's number 11. So we have CH4, we got 1 carbon. So we got 1 carbon. We have 4 hydrogens. Here we have 3 plus this 1, there's 4. We have 2 bromines. We got a bromine there and a bromine there. So far this one looks just fine. So everybody's 1 to 1 to 1 to 1. And just as many as we needed for each. Just had to think about hydrogen in those 2 portions over there to get that one. Let's try this other one. So magnesium, there's 1. Magnesium, there's 1. Hydrogen, there's 2. So we need to come over here and fix that. Give hydrogen a 2. This gives us 2 bromines, but we already have 2 bromines. So this is going to be a 1, 2, 1, 1, and then it'll match down here. So we already know the other answer by default, but let's practice it. We have 3 carbons, so we come over here with 3 carbons. We have 8 hydrogens, so we need to take 4 times 2. That gives us our 8. We have 1 oxygen here. We have 2 more oxygens, so that together makes 3. Over here we have 3. So we have 3 oxygens there. We have 8 there. Actually, 8 hydrogens. We have 4 there. And to make that match, we're going to need a 3 here. So that gives us our 6 plus our now 7, and then we have 7 over there. So 7 oxygens before, 1 here, now 6 there, so there's 7 instead of now 3. And then again, 3 times our imaginary 1 gives us 3, and then 4 more gives us our 7, and now those are equal. It's a little trickier one there, but in the end it balanced like it should. As we finish this homework, this last section just comes straight off the solubility table. So if you're water soluble, look for the K+, the Na pluses in particular. Look for the nitrates, maybe the acetates in particular. Look for ammonia in particular. So all of those, gonna love to be water soluble, always. Definitely gonna stay away from water insoluble. So when you look for those, look for potassium, look for nitrate, look for an acetate, look for potassium, and then they only have a few left, and those are the ones you have to look for with your solubility table. So I'll just refer you back to this. If they're in yellow, they're water soluble. And if they're in this left little corner column, they're in water solubility as well. But there are some exceptions, and that's where those questions are going to aim at. So if you're over here, now you're going to be water insoluble, just like over here. So it's almost like here's water soluble, and then here is water insoluble. And we'll catch you next time.